All right, today we are going to talk about compositions and inverses. It is, at the beginning with compositions, very similar to when we talked about function notation in Math 3. You are essentially going to be given a function like f of x equals, let's just start with x squared. And you're going to be given a second function, g of x equals, let's do x plus 1. When you have a composition, you're going to be asked to substitute one function into another. So one function becomes the input for another function. So the notation for that looks something like this. F of g of x is what the question's going to look like. So that can look a little scary. So we're going to take it back a step and let's, for your notes, write down that this is a composition of functions. So since that looks a little scary, we're going to, like I said, take it back a step and think about what it looks like for normal function notation. So if I asked you to do f of, let's say, 2, remember that 2 is your input. So this is the input. And when you're asked to do an input, all that means is that you want to input the 2 in place of the x right here. So whenever you have an input, you want to substitute that in for the x. Okay, so we are going to take that 2, put it in the input. So now that means we're going to do 2 squared, and our result ends up being 4. If we had, say, f of -4, something like that, you would then take the -4, put it in the input. Okay, so then you'd have -4 right here. And then you would get -4 squared, which would then give you 16. So a composition of functions simply means that you would take this entire function, x plus 1, and you would substitute that whole function into the input. So if I ask you to do f of g of x, you are going to take this entire function, g of x, which we are given in the problem is x plus 1. So that means I want to take that function, x plus 1, and make that our input. So I'm going to input that into the function f of x. And so we now are going to put that in place of x. So instead of x squared, we are now going to make our input x plus 1. And so we are going to make that x plus 1 squared. So just like we did with the 2 and with the -4, our input here is x plus 1. Now the problem's not done yet because we do need to simplify that, and we are going to go ahead and multiply that out as x plus 1 times x plus 1. And so we need to go ahead and distribute everything. So we're going to do x times x times 1, 1 times x, and 1 times 1. And so we're going to get x squared plus 2x plus 1. So this would be our final expression for the composition of f of g of x. Now, so that's the general idea behind composition of functions. We do also have other ways of noting that. So notation for that, we can either have f of g of x. That is the same as saying f in an open circle that stands for of, and then g. So f of g, do not say fog, it's not fog, but f of g, and then of x. So you can really use either notation there. Okay, so there's several different problems that you could do. You could have this with x's like what we just did. You could also have numerical expressions. So anytime you have these problems, though, you are going to be given functions. So let's do another one real quick. We could have f of x equals square root of x plus 1, and then maybe g of x equals, let's go with x plus 3. So in a problem like this, I could ask you to find f of g of, let's do -3. So you can be given a numerical value as well. So if you are not comfortable with the f of g notation like this with the circle for O, you are more than welcome to rewrite this as f of g of -3 like that. You do want to follow order of operations, and you want to go ahead and do what's inside the parentheses first. So you want to do this stuff first, and do do g of -3. So go ahead and do that part first. So kind of off to the side, if you want to think, what is g of -3? So g of -3, -3 becomes your input. So you want to input -3 into the g function. So -3 plus 3 is going to give you an output of 0. Come back to the original problem, and the original problem now says f of 0, because we just found that g of -3 is 0. So f of 0 is now what we need to evaluate so that we can finish this problem. So now we're going to go to the f function, and we are going to substitute in 0 for our input. So now to do f of 0, we are going to do square root of 0 and then plus 1. And so we get the square root of 1, which is 1. So that is our final number for this problem. Okay, we can also leave this with variables in the problem like we did in the first example. We could also ask you to do domain and range questions with this, all kinds of things that you could be asked to do. So let me ask another question here. If we did f of g of, let's see, -10. If we do g of -10, g of -10 here, if we just start on that part, g of -10, do this off to the side, g of -10, -10 for our input gives you a -7. So far everything's the same as part A. You're probably wondering, why are we doing this? If we come back here and do f of -10, what is the problem with doing f of -10? Well, if we do f of -10 here, we get the square root of -9. Well, if you remember anything from math 3. Square root of a negative gives you an imaginary number. So this one is a no can do. So this one is a no solution. And that leads into my next point. If I were to ask you for this composition, what is the domain I obviously don't write as neat on this computer as Miss Willis does. What is the domain of f of g of x? There are going to be some restrictions. So a lot of you, if I were to ask this question, would probably find f of g of x, and you would probably go ahead and do that composition, and you would substitute g of x into f, and it would look something like this. Here's g of x, x plus 3, and then the plus 1 from our original f of x, and you would get square root of x plus 4. Okay, and so then you would solve that, and you would graph it, and you would look at that domain. And so you would say the domain is -4 to infinity, and that's lovely. However, if we have a different set of functions, like, for example, f of x equals x squared plus 1, and g of x equals the square root of x, things get a little bit more tricky. All right, so let's look at f of g of x. When we look at f of g of x, and we take our g of x and substitute it into the original, what happens? Well, f of the square root of x, because that's our g of x, when that becomes our input, when we square the square root, these symbols, those are inverses of each other, so they're going to cancel each other out. And it appears, if you're not really thinking, it appears that this composition just becomes a line. And if you're not really thinking about it, we would say, well, a linear function has a domain of all real numbers. However, if I asked you to do f of g of -2, can we substitute -2 into this expression here? And the answer to that is no, I cannot take the square root of a negative. So in reality, this composition right here does not have a domain of all real numbers. So what you have to do to answer a question of what is the domain of this composition is you have to actually look right here and think about what you are allowed to substitute into the composition before it has been simplified. So before it's been simplified, I'm only allowed to substitute in x values from 0 to infinity. So the domain of f of g of x is actually 0 to infinity. All right, the second topic we're going to briefly discuss. Remember, the rest of the stuff we are going to practice and discuss in class. But the second topic we're going to discuss today is inverses. Inverses is a topic that we talked about in Math 3, so hopefully this will just be a quick little review. All right, inverses is when you have a function like this, we'll say, and then when you reflect over the line y equals x. So it would look something like this. These two functions, sorry, this function and this relation are inverses of each other. And it's all about reflecting over the line y equals x. So if you see that a graph has been reflected over the line y equals x, then the two graphs are inverses of each other. So that's the key idea there. If you have the function as an actual equation, then, and you need to find the inverse, then kind of the key idea, because of this reflection of the line y equals x, the key idea here is that the x and y are switched. And again, we discussed this in Math 3. So if you want to find an inverse algebraically, this is kind of the idea, is you're going to switch x and y. If you're finding it algebraic or graphically, you're still going to do the same thing. You're going to switch x and y. So you can work on either of those in class. I'll go over an algebraic one here and discuss some of these ideas. So as an example, if we have y equals the square root of x minus 2, and you were asked to find the inverse. So the key idea, again, is that you're going to switch x and y. So I'm going to take the y, literally make it an x, and the x, and make that a y. Everything else stays right where it was. And then you want to solve for y so that you can find out the equation of the inverse. So to get y by itself, you are going to have to get rid of the square root sign. So the inverse operation of square rooting is to square, so we are going to square both sides. So this side becomes x squared, and then here we get y minus 2. And then we need to add 2 to both sides. All right, now the issue with this, which you will have to be careful with, is that my original problem up here is a square root graph. If you think about it, we're always having to think in pre-calculus. The original, if I were to graph it, would look something like this. It's a square root graph shifted to the right 2. So something like this. My inverse is a parabola shifted up 2. Okay, and so the issue here is, if I go back to what I first drew up here at the top, okay, I said that an inverse has to be a reflection of the original over the line y equals x. If we look at what we have here, my original is kind of a sideways half parabola, but my inverse ends up being a whole parabola. So that's a problem. They're supposed to be the same shape, just reflected over the line y equals x. So here's the line y equals x. All right, my answer is supposed to look like this. It's supposed to be a little half parabola. And I got a whole parabola. So this answer that I got here is the right kind of shape, but I have too much of it. I'm only supposed to have this right-hand side. So to get my final answer, I need to restrict how much I have here. So we restrict the answer by saying that I have y equals x squared plus 2, but for only the domain of 0 to infinity. So we only want this right-hand side. So then it's the right shape to match the reflection of the original problem. Now that doesn't always happen, so you don't always have to worry about that. I picked this example to go over because it was weird. That usually only happens when you have a square root graph and then you come out with a parabola. So this is a really weird one. Okay, I think that's going to be it for today, and then we will go over a few more things in our notes next time in class, and then we will do some practice.